Welcome back to Advent of Code 2016, day 19. An elephant named Joseph. The elves contact you over a highly secure emergency channel. Back at the North Pole, the elves are busy misunderstanding white elephant parties. Each elf brings a present. They all sit in a circle, numbered starting with position 1. Then, starting with the first elf, they take turns stealing all the presents from the elf to their left. An elf with no presents is removed from the circle and does not take turns. For example, 5 elves, 1, 2, 3, 4, 5. Elf 1 takes 2 is present. Elf 2 has no presents, is skipped. Elf 3 takes elf 4 is present. 4 has no present, is skipped. Elf 5 takes 1, 2 presents. Neither 1 or 2 have presents. Both are skipped. Elf 3 takes 5, 3 present. So with 5 elves, the elf that sits starting position 3 gets all the presents. With the number of elves given in your puzzle input, this one, which elf gets all the presents? So we have input, test is 5. Let's just do cleanup, and then we want to we could just simulate it naively. We could just make a list. But then if we do a list of 5, we would have a list with 3 million elements here. Let's say n is this number. Test now, so 5, so 5. Up 1 into each. And we have elves. So each elf has a 1. And then we pass the presents. So 1 takes 2's presents. So I can go elves. Next equals elves dot indices dot each index. I go and take the result is elves I plus 1 when else, and I have the last index, then it's 0, or it's like 1. That's the result. Then I have next. Let's check that. Next. Wait, I didn't really steal anything now. It's myself. Help. Do is just neighbor. Myself plus my neighbor. And then I print it. Okay. Uh-huh. As soon as I steal my neighbor's present, he doesn't have it anymore. So I have to make it mutable and update him. Can I do that? Maybe just even for each. I can even update myself. And there's no next, there's just elves. Okay. Kind of didn't work. Let's see. This one should steal this present. Maybe we can print every time and see what happens. Okay, yeah, this one did steal this guy's present. If you don't have a present, you get skipped. Also, an elf with no present is removed from the circle. Oh, so maybe I shouldn't mutate the list then. I'll just make a new list every time. And my index just goes. Let's just do like this. While elf size I will actually this will be a thing that will change. We will do this. I check the neighbor, slashing 0 else's I plus 1. Then I make a new elves. That is elves sublist 0 to me. I wonder if I can remove addIndex or something. And then don't. It's just a MutableList that I just remove stuff in. And then it's smaller, so every time I remove someone. And else. And update I equals just need the same. So I equals neighbor. Does that work? Yeah, I just don't have the original index anymore. Hmm. Name. Elf with name equals okay, we have an elf. So then okay, so I just get the present from the neighbor, get my presents, I add them, and add them to myself. And that's what myself is. Then I remove the neighbor. And then I have this issue. Just delete this. Okay, so I have name 1. It's 5 presents. They all have name 1. Cool. Name I. Okay, so name 2 has 3 presents. It's gonna have 3. Okay, let's do this. I have it here, input. pretty long lists probably. Let's try this again. Okay, takes mega long. Wonder what it takes long at. I can't. Hmm. I know that in every pass through, let's say one, 2, 3, 4. In every pass through, this person steals the presence of this one. And then he gets eliminated. And then this one just steals from here. So I could do this part and this part at the same time. I could just steal. Um, this is a run where we think. Hmm, Let's see what we could do. The first round, we have an even amount. Then the first round would be basically this. On 1, 2, 1, 3, 1, 4, 1. Just wondering if this happens. I always set as neighbor. Remove. And ignore this. And then do it again. Okay, whatever. Let's just finish the code. Basically, first one stays, third one stays. Mm, mm, uh, let's say there's an odd one. He then steals from 1. So it's 2 equals 1. Then Now the even part. Actually, we can take first elves presence. We can say last. He remains. Name says presence. Make this mutable. Okay, let's try test 3. Still correct. So it does this in one step. 2, 2. 2 has 2, 4 has 2, and then only 2 has 4, which is then 3, yeah. Although, wait, why is it 4? Should be 5. Okay, that's weird. Let's check again. So what happens? Print line elves. So we have 0, 1, 1, 1. No, how does it work? Just do presence. Yeah, it's easier. 0, 1, 1, 1, 2, 1, 2, 2. Shouldn't we have 0, 2, 2, 2, 4? Then against the 2 from him, so he would get 3. And this one disappears. So then we have 2, 2, and 4, 3. So we're just missing this. Here we have a 0 to 2, 2, 4, 2. We want, I really want this, not last one even. Whatever. Result. No. Result dot last is, let's check again. Result has 4 in it. Ah, yeah, okay. We leave it in. It duplicates its own presence. That's wrong. Uh, I mean, the whole duplicate part doesn't fully work. But yeah, first of all, let's say we want this to be else. This does remove the sublist to this to the last index. Which there's one less. Now we use this. Okay, let's do this. 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 2, 2. We need 4, 3 there. And let's go here again. Yeah. I just want this to last. No. We want 4, 2. Ah, yeah, this to last. Right, do I see this? Yeah, this to last 4, 1. That's presence 1. Just let's say it's rounds 2, it's kind of wrong, but whatever. And then, ah, yeah, okay. And we just add that to the result. Add. This works for one example. That is the last guy weird. And whoever steals from the last guy is always weird. So I can go around one less. So I can basically do this algorithm the first at the end, and this for the first, let's say, whatever, 80% of the list. And it's very easy for Eve. Wonder if I can just do this. Let's just make another one. And we take even even part. Ignore the odd part. Okay. What we can then do is just 50% would help a lot. Let's just take 80%. Something like that, as long so then I first do that. Actually, split the list, right? So first half is elves dot first n elements. And we go through the rest of the list, which is okay, well, neighbor. Mm, okay. And then combine again. Okay. I really want to start at 0. Large compact tile. What happened? Ah, okay. It's important. Your number is point. So if it's 11, if it's 12, we go to 6, and we're happy with 6. And if it's 2, if it's 11, then we go to 5, and we're happy with 5. 5. Not happy with 5, so we want to go to 6. We take this, take the last, minus even n, continue at we just continue. We just go here and take the next ones. Stuff. Okay. And we always handle the last one correctly. Does it work? Let's see. 2 as 5. Number 3. Okay, cool. Let's see what happens if we do the proper one. Printing too much or 2%. That's not true. Oh, wait. After we compact it, we need to set false. And then once we flip over, we know the next one. Okay, let's do it's not false then. Wonder why it's 3. Doesn't it choose the midpoint to be 15? And then it only compacts that part. Okay, we need more. We know that we're greater than 10. So we can choose a midpoint way higher. We can go what's the problem? Double. Round a double. It's round. Okay, good. Now we're halfway. That's a better Weird. What happens now? Let's check it again. And now we have half the size. Then second half, 300,000. Oh, the next n is not 300,000. The next n is first half dot size plus 1. Or dot size, actually. Yeah, that looks better. Let's check the test. 3. I am always printing. Okay, 3 is correct. Let's just trust it. And that's correct. Let's see. Realizing the folly of their present exchange rules, the elves agree to instead steal presents from elves directly across the circle. Elves across the circle, the one on the left, which the stealer is stolen from. Wow. The other circle, the other rules remain unchanged. Okay, I think you need a different algorithm for that, but let me explain this. Solution for part 1. We have elves. We mark them with their initial position and I'll give them 1 present. Then we say that we take the first 90% of the list, and this is kind of where we get the midpoint. We get an even amount of interest from the first 90%. So we have to calibrate this midpoint. Then we can process this even amount by just duplicating the presents, because the first ones will always, if this is the row that they steal, then 1 steals from 2, the 3 steals from 4, 2 and 4 are eliminated, 6 and 8 similarly. We can always just skip 1, filter them out, and duplicate the presence of the current one. Use it to the end. We split the list. And then we handle basically this last part separate, because this part is always the same, the first, and then the last part gets handled. Second half, which is the rest, have size minus even n. We update our index to start again at the end of the first half, because our paths are already processed. And then we just process it the way we initially had it, where check the neighbor if we're the last one, then we want to fetch from the first one, otherwise we fetch from our neighbor next to us, and then we just update this list. The reason this is fast is because we skip 90% of the computation here by doing everything once. Just cut the list in half and duplicate all the spots, and only do the work at the end. So now we want to steal from opposite, which means In a smaller example, it's a bit confusing because you just keep sweeping from opposite. In a large example, we still have a similar setting, I feel like. One thing I'm realizing is we don't actually need to add the presence. We just need to walk through the list and eliminate elves. Last one, sending will have all the presents. So all this work on adding the presents is kind of nonsensical. See what happens if I remove it. Maybe just get the elf. I'm curious if I can just make it work. The original way we had. Just copy everything. And then just delete all the extra stuff. This is the lower version. There's also not any objects. Hmm. Don't make it mutable. She's finding the neighbor then. So the solution for part 2, the naive solution works, but it's just very slow. So I was curious how to properly do it and checked some solutions. And one idea that seemed to work is to go split the list into 2 lists. We have this example with 5 elves. You have 1, 2, and then 3, 4, 5. So top and bottom list, and then kind of see what happens. And the algorithm is quite simple, but I didn't really understand it. But if you go through some examples, it makes sense. So in this scenario, opposite of 1 is 4 and 3. So the left one is 3, so 1 steals from 3. And what's left is 1, 2, 5, 4. And then 2 steals from 5. Then 4 steals from 1. and then 2 steals from 4 and wins. So there's not really a pattern, but if you look at a bigger example, you kind of see, kind of can find a pattern. So here's kind of the same, just that I have more in the top list and then in the bottom. So the first thing is I remove 5, then 2 removes 7, then 3 removes 8, and then 4 removes 1. So it kind of goes around the circle. If I want to only use the operations removeLast and removeFirst, I can get somewhere by rotating the list. So adding that idea into the mix and going through the same example, I can see that I remove 5, then rotate. So what I get is put the 1 to the bottom, to the 6 to the top. Then I have 2, 3, 4, 6, 7, 8, 9, 1. And then 2 removes 7. First I remove the last from the first list and then the last from the second list. Then I rotate similarly, I remove from the first list. And then I remove from the second list. If I rotate every time, I always just remove the last from one of the lists. At the end, only 9 remains in this case and stays. So that's how I can do it. I just have to make sure that the first list has all the items. Let's check. There's more items now here. Midpoint earlier, maybe I can do it again. Okay, so top has 3, 1, 2, 3. Bottom has 2, 5, and 4. Then basically I just have to check. Look at my example. I remove 5 because the top list is longer. And if the top list and the bottom list are the same, I remove from the bottom list. So I can say else bottom not remove last. And then I want to rotate. Delete all this. This. Rotate the lists, which means I take the first one from the top. So the first round, is done, what happened? I end up with just make the example 4. 1 removes 3, and then we rotate. Then we have this. Remove my example. Delete it. 1, 2, 5, 4. Top. Well, at this point, I should have 1, 2, 5, 4. And then I rotate to 4, 1, 5. Yeah, that's what I have. Okay. Then we can do while loop. Okay, so now 2 remains. And if I use input, very slow. I was curious about 9. Oh, this 9 remains. Yeah, that's what we had in our example. Okay. Why it's so slow now? Okay, I just ran this. Still not fast, but let's see if it's correct. And that's it. Okay. So basically, pattern matching and looking at examples. What's the solution? We still don't know how to do it fast. I'll leave that for another time.